Hello students, in this present video I will explain the properties of carboxylic acid. So let us see the properties. Let us see first the physical properties. Now carboxylic acid can form intermolecular hydrogen bond, and therefore it exists as dimer. That means its effective molecular mass becomes double than the normal molecular mass due to presence of this intermolecular hydrogen bond. And as because it is carboxylic acid ionizes in aqueous solution, so it is usually soluble in water, but its solubility decreases with increasing size of the alkyl group, and higher carboxylic acid are not readily soluble in water. Next come to the chemical properties. Number one, acidic nature. Carboxylic acid is acidic in nature, and therefore it gives the characteristic reaction of acid, like reaction with metal gives salt and hydrogen gas. Reaction with alkali gives salt and water. And the presence of carboxylic acid is identified in its by its reaction with sodium bicarbonate. With bicarbonate, it gives strong effervescence due to formation of carbon dioxide. That means carboxylic acid, when given as a sample, unknown sample, if we react it with sodium bicarbonate, it forms strong effervescence due to formation of carbon dioxide following this reaction. And therefore, in practical chemistry also, we use sodium bicarbonate for identification of carboxylic acid. Now, if we compare the acidic character of carboxylic acid, comparison of acidic character between different carboxylic acid, then we need to explain through its stability of the conjugate base. That means carboxylic acid in aqueous solution ionizes to form this carboxylate ion, which is resonance stabilized in this way, and its the acidic character of the carboxylic acid depends on the resonance stability of this carboxylate ion. Higher the stability of carboxylate ion, higher will be the acidic nature of the corresponding carboxylic acid. And this resonance stabilization depends on the electropositive nature of this carbonyl carbon of the carboxylate ion group, carboxylate ion. Now, suppose with this alkyl group here, if there is any electron withdrawing group present, then what will happen? There will be a pool of electron from this carbonyl carbon, and therefore the electropositive nature will increase, and the resonance stabilization, corresponding resonance stabilization, will also increase. That means the resonance here, this resonance will be more profound. And if there is an electron donating group with this alkyl group here, if any electron withdrawing group is there, or rather any electron group withdrawing group is, donating group is there at this carbonyl carbon, then due to donation of electron, the electropositive nature will decrease for this carbonyl carbon, and the resonance stabilization will also decrease. And therefore, in another way, suppose if we want to discuss the acidic nature, we can explain through the ionization constant of the carboxylic acid. Here is the equation for the ionization constant of the carboxylic acid. Here in the numerator, concentration of the carboxylate ion, this one, and the hydronium ion, and in the denominator, the concentration of the carboxylic acid. So higher this Ka value, that means higher is the concentration of this hydronium ion, that means the carboxylic acid is dissociated more. So higher the Ka value, higher will be the acidic character of the carboxylic acid. And on the other hand, if we take the minus log of this Ka value, that is called pKa, if Ka is higher, then pKa will be lower. Therefore, we can state that higher the Ka value and lower the pKa value, then higher will be the acidic character of the acid. Here, let us find some examples. I have already given the order of acidic character here. Say it is fluoroacetic acid, chloroacetic acid, methanoic acid, and acetic acid. You can follow here fluorine is having minus I effect and it withdraws electron. Now the withdrawing power for chlorine is little less than fluorine due to its lower electronegativity than fluorine. In case of methanoic acid, there is no such effect because hydrogen do not play a role like that. Whereas methyl group here in the acetic acid donates electron to the carbonyl carbon, and therefore the corresponding conjugate acid will conjugate base will be less stable. Therefore, this is the order of acidic nature, as because the corresponding carboxylate ions will also be more stable. Here we can follow it is due to the presence of electron withdrawing group and the presence of electron donating group that actually explaining this order. Similarly, here in case of aromatic acid, we can follow that paranitrobenzoic acid, there is minus R effect of the NO2 group that withdraws electron from the ring, and therefore from the carbonyl carbon, the electron is coming towards the ring. So the carbonyl carbon is becoming more electropositive, and its corresponding carboxylate ion will be more resonance stabilized. Now, this withdrawal effect is not there in case of benzoic acid, whereas paramethyl benzoic acid, it is having plus I effect, it donates electron into the ring. Therefore, the carbonyl carbon of the corresponding carboxylic acid is having a donation from the ring towards this carboxylate ion, carbonyl carbon of the carboxylic acid group. Therefore, its acidic character will be less. And this donation is further more in case of this methoxy group, which is playing a role of plus R effect. That is, it donates electron by resonance. So therefore, ring will be more electron rich and the electron will be more coming towards the carboxylate ion, and therefore the acidic character will be further less. Hence, this is the order of carboxylic, acidity of the carboxylic acids. Now, let us look into the reaction involving cleavage of carbon-oxygen bond. Here, the characteristic reaction is where the bond between this carbon oxygen, that means it is broken and this OH group is becoming free. That means the derivatives of acids are formed when this OH group is replaced with halogen. It is giving rise the acid halide. If it is replaced with NH2, then it is the amide CONH2 group. It can be replaced with alkoxide group, or dashed here it is written, giving rise the ester, and it can be replaced with this acetyl group, that means RCO group. This is for giving rise the anhydride. So these are the four types of derivatives can be prepared from carboxylic acid, and these reactions are the characteristic reactions where the carbon oxygen bond here it is broken. So first of all, we can prepare acid halide when carboxylic acid is reacted with uh, phosphorus halides like phosphorus pentahalide, pentachloride, phosphorus trichloride, phosphorus tribromide, and this tribromide can be found from red phosphorus and bromine. So what is happening? The OH group is replaced with the corresponding halogen, giving rise this acid halide. As an example, if we react here, one more thing is that if among these halogenating agents, thionyl chloride SOCl2 is most suitable one, because the in that reaction the byproducts those are formed are gaseous. Therefore, the corresponding acid halide is found in it is obtained without the presence of these byproducts. Its collection will be more easier. Hence, as an example, ethanoic acid treated with thionyl chloride giving rise this ethanoyl chloride, commonly named as acetyl chloride. And benzoic acid, from benzoic acid we can get benzoyl chloride when treated with thionyl chloride. So in this way acid halide can be prepared. Now next come to the second reaction, this one, where uh, amide is formed from carboxylic acid. Now first, for that, carboxylic acid is treated with ammonia that gives rise the ammonium salt of the carboxylic acid, and when it is heated due to dehydration the amide is formed. So ethanoic acid as an example reacting with ammonia forming ammonium acetate, when it is heated it gives ethanamide by the dehydration process. Similarly, benzoic acid reacting with ammonia to form ammonium benzoate. This is ammonium benzoate, PaHCOO minus NH4 plus. When it is heated due to dehydration, we get PaHCONH2, that is benzamide. Its structural form is benzene ring with CO and NH2 group. And there comes a special compound formation when this phthalic acid, that is uh, 1,2-dibenzoic acid, it is actually in the benzene ring the two orthopositions are having carboxylic acid group reacting with ammonia forming this ammonium salt of phthalic acid. Now when it is heated then two molecules of water are removed from this ammonium salt giving rise this phthalamide. It is CONH2 and CONH2. It is called phthalamide. And on strong heating from this phthalamide, another molecule of ammonia, here you follow that, it is being removed. And due to that, we are getting a cyclic amide. It is called phthalimide. So from phthalic acid, we can prepare phthalimide when reacted with ammonia followed by strong heating. So these are the reactions that are explaining the preparation of the derivative, acid derivative amide. Next, we come to the preparation of anhydride. As we know that anhydride is a substance that when combines with water forms carboxylic acid. Therefore, uh, uh, on the opposite, if we say that from the two molecules of carboxylic acid, if one molecule water is being removed, then we can get the anhydride. It can be represented as this RCOO C double bond O R. In condensed form, it is RCO whole 2 O. So this dehydration is possible in presence of dehydrating agents like P2O5, which can give the reaction in dry condition, and also in presence of concentrate sulfuric acid, which is acting as a dehydrating agent to remove water from the carboxylic acid. So here as an example, if we remove water from two molecules of ethanoic acid, we can get uh, ethanoic anhydride, that is commonly known as acetic anhydride, and in short we write it CH3CO whole 2 CH3CO whole 2 O. So in this way anhydride can be formed. Now, next is preparation of the ester. This is another acid derivative. It can be obtained when carboxylic acid is reacted with alcohol in presence of concentrate sulfuric acid, and due to heating, what happens, from the acid and the alcohol one molecule of water is being removed. We can follow that here the carbon oxygen bond of the acid is broken and the oxygen hydrogen bond of the alcohol is broken to give rise this ester. So we can follow it is RC double bond O O R dash. This is the product, and during its name we name the first this alkyl group known as alkyl, and then this alkanoate group. So the name of the ester is followed as alkyl alkanoate. Now, as an example, when ethanoic acid and ethanol is heated in presence of concentrated sulfuric acid, then water is being removed to give rise this ethyl ethanoate, acetyl acetate. Ethyl acetate. It can be stated as, in IUPAC it is ethyl ethanoate. In common name it is ethyl acetate. Likewise, this thing, this this is salicylic acid. It is when treated with methanol in presence of concentrated sulfuric acid, it gives rise methyl salicylate. This methyl salicylate is also known as oil of wintergreen, which is usually uh, used in pain removing balms. So it has got a characteristic pungent smell. So this is also an ester. Now, ester is a compound that is found, that is having a fruit-like smell, and it is found in all the fruits. So all the fruits, those are having characteristic smell due to presence of particular ester. Here we can follow the mechanism of this esterification process. First of all, in presence of the sulfuric acid, concentrated sulfuric acid as dehydrating agent, we are using the protonation of acid giving rise this, ionization of the acid giving rise this H plus, which helps in protonating this carboxylic acid. The lone pair is attacking the H plus ion, forming this intermediate. Now next, this alcoholic group, the lone pair is acting as a electrophilic center, so it is attacking this nucleophilic center, it is attacking this electrophilic center of this carboxylic acid intermediate, then giving rise this intermediate where a proton transfer process is taking place. That means hydrogen H plus ion is being removed from here, and this H plus ion is taken away by this OH group, giving rise this intermediate, and therefrom due to dehydration we can get this intermediate, and after deprotonation we get the ester. So this is the mechanistic way of preparation of the another acid derivative called ester. Now let us find reaction of carboxylic acid group, where the corresponding reaction is taking place due to this whole COOH group. First of all, it can be a reduction reaction, lithium aluminum hydride or catalytic hydrogenation of, or using B2H6, we can reduce carboxylic acid to alcohol. Clear? Now, as an example, ethanoic acid can be reduced to ethanol. This benzoic acid can be reduced to this benzyl alcohol. And then second type of reaction, this reaction we have already studied in class 11, that is called decarboxylation. That means carboxylic acid when heated with sodium hydroxide, it first forms the sodium carboxylate, and after that when it is heated with soda lime, mixture of sodium hydroxide and calcium oxide, then decarboxylation takes place. We can follow that this is the part being removed, and this R and the H is combining to form the alkane. Hence, we are getting an alkane from the carboxylic acid with one carbon less. That means this reaction can be used for descending of carbon chain. As an example, here ethanoic acid gives rise methane. Benzoic acid, this carbon will be removed when heated with soda lime, giving rise benzene. Now another reaction, this is also we have learned in class 11, it is Kolbe's electrolysis. Carboxylate ion, that is the potassium carboxylate, when heated, electrolyzed, then we get an alkane. Here we can follow that from the two molecules of the salt of the carboxylic acid, this alkyl group is combining to give rise the alkane. So in this process, always we get an alkane with even number of carbon atoms. So when this potassium ethanoate is electrolyzed, then at the anode we get the ethane. That means this two CH3 group is joined to form this product ethane. Now, if already there is the carbon-carbon bond is joined in case of potassium succinate. So what will happen? These two carbon dioxide molecule will be removed, giving rise ethene as the product. By this process, by this Kolbe's electrolysis, we can even prepare alkyne when this potassium salt of maleic acid it is electrolyzed, then two molecules of this carbon dioxide molecules are removed, so there will be a triple bond formed, giving rise this ethane. So in this way, we can get alkane, alkene, and alkyne by Kolbe's electrolysis process. Now next come the very important reaction, which is namely as HVZ reaction, Hell-Volhard-Jelensky reaction, where when a carboxylic acid is treated with uh, halogen in presence of red phosphorus followed by hydrolysis, then at the alpha position the halogen substitution takes place. So when ethanoic acid is treated with this chlorine and red phosphorus, then chloroacetic acid is formed, and this reaction can have several applications, like this OH group can be replaced, can be substituted when treated with aqueous alkali, and followed by acidification. Otherwise this acid group will remain as salt, so giving rise this 2 hydroxy ethanoic acid. If we treat it with KCN, then cyanide will replace the Cl group, giving rise this this intermediate cyanide derivative. And when it is hydrolyzed, acid hydrolyzed, the cyanide group will be converted to carboxylic acid, giving rise this malic acid. So another way, when if we do the substitution at the alpha position of this acetic acid, alpha hydrogens are substituted with halogen. 2 moles of halogens are coming here. So these halogens can be substituted with OH group when treated with aqueous alkali, followed by acidification, giving rise this intermediate product. Now this carbon is having, this alpha carbon of this acid is having 2 OH group, where from 1 molecule of water is being removed when heated to give rise this uh, compound, where you can follow that this methyl group it was in the acetic acid is converted to the aldehydic group, which can be oxidized to form the carboxylic acid. Therefore we can get oxalic acid from acetic acid. So in this way, some application of this HVZ reaction can be carried out. Next, the next reaction is the electrophilic substitution reaction. We can follow that carboxylic acid group is an electron withdrawing group. It withdraws electron from the benzene ring. So carboxylic acid is a meta-directing group. Therefore, in electrophilic substitution reaction, the electrophile enters at the meta position. Therefore, on nitration, when carboxylic acid is nitrated, it gives meta-nitrobenzoic acid. On halogenation, we can get meta-bromo or meta-chlorobenzoic acid. Now, in case of benzoic acid, the Friedel-Crafts reaction is a bit difficult, because we know that any electron withdrawing group deactivates the ring towards the electrophilic substitution reaction. So they are much difficult compared to nitration and halogenation. So these are the possible reactions, as I have explained here, for carboxylic acid. Thank you.